Thermodynamics is one of the main questions in paper one, and usually it comes in the form of the Born-Haber cycle. Before I start talking about the Born-Haber cycle, we need to go quickly over Hess's cycle, which is mainly in paper two, but we're going to apply the principles of the Hess's law into the Born-Haber cycle. So what is Hess's law? Hess's law states that the total enthalpy change for a reaction is the same no matter the route taken. So if you have one route like reactant, react to give you certain products, whether it goes directly from reactant into product or whether it goes through an intermediate where reactant gives you an intermediate and then the intermediate goes to give you a product, for each of these reactions, there will be a certain enthalpy change. Now we have two different routes. The total of route one will equal the total of route two. Route one will be the one in one direction, as we see from the arrows. This is the orange one. Route two will be the two steps which are in the opposite direction, which go together in opposite direction to route one. So they go in the same direction. So the total of the enthalpy change of route one will equal the total of the enthalpy change of route two. If we have any of these missing, we can rearrange our equation to find the missing enthalpy change. So the types of enthalpy change, there are several types of enthalpy change. I will be focusing now on one of the important ones, which is the standard enthalpy of formation. Standard enthalpy of formation is the enthalpy change when 1 mole of a compound is formed from its elements in their standard states under standard conditions. So formation can be for organic, covalent compounds or for ionic compounds. And it's from the elements and their standard states under standard conditions. So for carbon, for example, it's always going to be solid, hydrogen, gas, oxygen, gas. How to build Hess cycle and how to build Born-Haber cycle. So we're going to build Born-Haber cycle using the same principle for Hess cycle. Quickly, how to do this using the enthalpy of formation. So if we have a reaction like this one, we have sulfur dioxide, hydrogen sulfide reacting together to give you sulfur and water. We have the enthalpy change for this reaction. We don't know what is the enthalpy change. We are not given the bond enthalpies for the different bonds of reactants and products. So we need to calculate the enthalpy change of this reaction using Hess's cycle. And we're going to do this using the enthalpy of formation. So we have first one the formation of the reactants from their elements, and the second one will be the enthalpy of formation of the products from their elements, which is basically the same elements. And now we have two routes, as we can see, based on the direction of arrows, and you can see that from the colors. So route one will be the two reactions which are in red, which go in one direction. The route two will be the one in blue, which goes in the opposite direction. Route one will give you the enthalpy of formation of sulfur dioxide and 2 times the enthalpy of formation of hydrogen sulfide because we have 2 moles. And route two, in addition, of course, to the enthalpy of the reaction, which is missing. Route two will be 3 times the enthalpy of formation of water, and this is an element, it has 0 enthalpy of formation. Root 1 equals root 2. When you put all the values that you are going to be provided with in the exam, there will be only one value missing, and you can find this value. Now, Born-Haber cycle, we're going to do the exact same thing. We are going to construct what is the Born-Haber cycle, applying the same principles for the Hess's cycle. So what is Born-Haber cycle and what's the purpose for this one? So Born-Haber cycle is basically for the ionic compounds. So we are trying to calculate or determine what is called the enthalpy of lattice formation, and these are for ionic compound. Why are we determining this or calculating that? We want to compare between the values we are going to get from the Born-Haber cycle and the value from the data book or the theoretical value. Theoretical values assume that all ionic compounds are pure ionic compounds. So there is something called the pure ionic model assumption. Pure ionic model assumption assumes that all ions are spherical and their charge are evenly distributed around them. However, ionic compounds are, the majority of them are not purely ionic, but they have some covalent character. So when you compare between the value you get from the Born-Haber cycle and the theoretical value, and then you can find that these two are different, then that means that the compound is not purely ionic, but it has some covalent character. If they are very close to each other, that means it's more like a pure ionic compound. Now, when we construct the Born-Haber cycle, there are certain enthalpies that we need to account for and we need to use. The first one is enthalpy of formation, which we talked about already. And then we have the atomization enthalpy. So when you have the elements, you need to atomize the elements, basically converting them into gaseous state, and they have to be one atom. So this is the enthalpy change when 1 mole of gaseous atoms is formed from elements in its standard state. So if it's solid in its standard state, we have to convert it to a gas. If it's a gas but a molecule, we have to convert it into individual atoms. And then we have the ionization enthalpy, which is ionization energy, basically. So it's the enthalpy change when 1 mole of electron is removed from 1 mole of gaseous atoms to form 1 mole of gaseous positive ions. So this is the ionization energy we talked about. We could use first and second, third, even ionization energy. We could use just the first one when we construct the Born-Haber cycle based on the ions we have. And then we have the electron affinity. Electron affinity is the same like the ionization enthalpy, but it's for gaining electrons to form gaseous -1 ions. So this is the enthalpy change when 1 mole of electron is added, this time not removed, to 1 mole of gaseous atoms to form 1 mole of gaseous negative ion. Remember that the first electron affinity is usually exothermic because the energy is released when when an electron is added. And then the second electron affinity, when you add a second electron, will be endothermic. This is because you are adding electron to an already negative ion. So we would need more energy to add the electron. And then finally, the lattice enthalpy. So the lattice enthalpy of the standard lattice enthalpy of formation or of dissociation. These are opposite to each other and they have the same value, but one is exothermic and the other one is endothermic. So lattice enthalpy of formation is the enthalpy change when 1 mole of ionic solid is formed from its gaseous ion. So this is different from formation because formation is the one that we form the compound from its element in their standard form. Here we are forming the ionic compound from its gaseous ions. It's going to be exothermic deformation because it involves a formation of a strong electrostatic attraction between the ions. However, if we are talking about the lattice enthalpy, the enthalpy of lattice dissociation, which is going to be the opposite one, then we are actually making the ions, the gaseous ions, from the solid. So it's going to be endothermic. It's just the same, but it's in the opposite direction. So it's the same enthalpy change, but it's going to be endothermic rather than exothermic. You need to be careful in the exam which one they want you to calculate. Now the Born-Haber cycle diagram. So I'm going to show you a quick diagram for one of the ionic compound, and then we're going to do it. I'm going to do it with you step by step because in the exam there will be some steps missing, and they want you to do the calculation. So this is the Born-Haber cycle diagram for magnesium chloride as ionic compound. So how would we construct that? What are all of these arrows? So let's start. So we're going to start at the bottom with the magnesium chloride. Don't forget the state sample, which is solid. And then we will start with the enthalpy of formation. Enthalpy of formation is the formation of the compounds from its element and their standard form. So we have magnesium, which is a solid, plus the two of the chlorine, so chlorine, which is gaseous in a standard form. And then the next step will be we need to do atomization. And atomization, we're going to do it step by step. So we're going to do atomization for the metal and then atomization for the non-metal. It doesn't matter which one comes first, and you can start with the non-metal. So I'm going to start with the metal first. So the atomization of the metal. So notice that now the arrow goes in the opposite direction, and then that will give us the magnesium as a gas, plus chlorine is staying the same as it is because I haven't done atomization for chlorine yet. So this is the enthalpy of the atomization of magnesium. The next step will be the atomization of the chlorine, and now we have the magnesium is still a gas. And then I'm going to convert the chlorine into atoms. So there will be two chlorine atom and both are gas. And now it's the atomization of chlorine, but it's going to be 2 times the atomization of chlorine because we have 2 moles of chlorine atoms formed. Following that, we need to start to ionize these atoms. So I'm going to start with the metal first. So we have magnesium. So I'm going to give the first ionization energy of magnesium. So here the ionization energy, first ionization energy for magnesium, and that will give us magnesium, which is a gas, as plus. The chlorine will stay as it is, as atoms, gas, and don't forget the electrons. And then we're gonna move on to the second ionization energy for magnesium because magnesium has to be Mg2 plus, so that will give you Mg2 plus, and it's gaseous, plus the 2. Remember that we haven't done anything with the chlorine yet. 2 atoms of chlorine plus 2 electrons now. And now we need to start working on the chlorine. So we have ionized the magnesium completely. So now moving on to the chlorine, now we need to give the electron affinity for the chlorine to give the chloride. We have 2 moles of the chlorine, so it's going to be 2 times the electron affinity of chlorine, and that will give us the magnesium will stay as it is as gas 2 plus, and the chlorine will change into 2 chloride as gases. Now we added 2 electrons, so we removed the electron from the equation. And now finally we have now the ions of both elements in their gaseous state. So with this is gonna give us, now we're gonna make the lattice formation. So this is the enthalpy of the lattice formation. It's this in this direction. So if you have the enthalpy of lattice formation missing in your question, now you need to construct the Hess cycle, or you need to do the equation or find your roots. So the first root will be only the enthalpy of formation because this is the only one that goes in this direction. All the other arrows go in one direction, as you can see this way. So they are in the opposite direction. So now this is the only one that has opposite direction. So this is going to be, this is the enthalpy of formation. So this is going to be root 1. All the other ones, we're going to add them together, will be root 2. And then we will rearrange our equation to find the enthalpy. Another important thermodynamic concept that we need to calculate, and very common in the exam, is the enthalpy of a solution. So what's enthalpy of solution? Enthalpy of solution is the enthalpy change when 1 mole of an ionic substance dissolves in water to form an aqueous solution, in which ions are separated and they are surrounded by water molecule, meaning it's hydrated. So when you dissolve a solid, an ionic compound, into water, there is some enthalpy enthalpy change. The sample for it is the delta H solution, sol, and the units is, as usual, kilojoule per mole. For example, if you have sodium chloride as a solid, that will give you sodium ion aqueous plus chloride ion aqueous. Is it exothermic or is it endothermic? It can be either. So it can be exothermic, which means the enthalpy of solution is going to be negative, meaning that more energy will be released when the ions are hydrated than the energy that is required to break the lattice. Or it could be endothermic, meaning that the more energy will be required to break the lattice than the energy that is released when they are hydrated. So the process of hydration itself is an exothermic process, and the process of breaking the lattice is an endothermic process. So whether a substance dissolves easily in water or not will depend not only on the enthalpy of a solution, but also on the entropy, which we are going to talk about next. So the key concepts for the enthalpy of solution, we have a certain enthalpies that we need to use to construct the Hess cycle for the enthalpy of solution. These are the lattice enthalpy, which we talked about in the Born-Haber cycle, or which we calculated using the Born-Haber cycle. So the lattice enthalpy here is the energy required, but here we are talking about the not the lattice formation, but the lattice dissociation. So the energy required to break apart the ionic lattice into gaseous ions. So this is the opposite of the lattice formation, and it's going to be endothermic. So we would need to supply energy to break the lattice bonds and to form the gaseous ions. So sodium chloride solid will give you sodium ion gas and chloride ion gas. And then we have the enthalpy of hydration. And enthalpy of hydration is the enthalpy change when 1 mole of these gaseous ions, which we just formed, dissolve in water to form hydrated gaseous ions. These hydrated gaseous ions are the ones that are going to be formed when we do the solution of the solid. So this is also this is always exothermic because water molecules form ion dipole interaction with the ions. So for example, we have a sodium ion gas will give you sodium ion aqueous. So this is the enthalpy of hydration, which is exothermic, and chloride ion gas will give you chloride ion aqueous. So there are certain factors that affect the enthalpy of hydration. What are these factors? First one is the ionic charge. So if the ion has higher charge, that means there will be stronger attraction to water. If there is a stronger attraction to water, that means the enthalpy of hydration will be more exothermic. So the value will be higher in negative charge. So for example, magnesium 2 plus has more exothermic enthalpy of hydration than sodium plus because it only has one positive charge. Also, the ionic radius. So the smaller the radius, the stronger the attraction, which is going to be between the positive ion and the water molecule. So smaller ions like lithium is hydrated more strongly than larger ions like potassium, for example. Generally speaking, ions with high charge density, meaning they are smaller in size and they have higher charge, they will have more exothermic hydration enthalpy. So let's construct the Hess cycle for the enthalpy of a solution. So we have sodium chloride as solid, and then it will change or be hydrated to give the sodium ions aqueous and chloride ion aqueous. This is the enthalpy change of solution. This is the one that usually they want you to calculate in the exam. You need to construct Hess cycle using the lattice dissociation enthalpy, which is the formation of the gaseous ion from the solid, and then the enthalpy of hydration, which is the hydration of the ions, the gaseous ions, to form the aqueous ions. As you can see from the direction of the arrows, these two in blue will be one root, and the one in yellow will be the opposite root. Now, there we're going to have root 1 will equal root 2, meaning the enthalpy of solution will equal the enthalpy of hydration of the sodium ion plus the enthalpy of hydration formation of chloride ion plus the enthalpy of the dissociation of the sodium chloride. Or if they provide you with the enthalpy of formation, it's going to be minus the enthalpy of formation, because enthalpy of formation will be in this direction in this case, and then it will go in the same route with the enthalpy of solution. So please take note of which one they provide you with in the exam. You will do the rearrangement and then you will calculate the enthalpy of solution. The enthalpy of solution is important to determine whether a certain ionic compound is going to dissolve in water or not, because some ionic compounds do not dissolve in water. So if the enthalpy of solution is exothermic or only slightly endothermic, the salt is more likely to be soluble in water. However, there is also entropy, which plays a role. So some solids have positive enthalpy of solution, but they are insoluble in water. So we will talk about entropy as well, because it also plays a role in the solubility in addition to the enthalpy of solution. But generally speaking, if the enthalpy of solution is exothermic or with a negative charge, the solid will be more likely to dissolve, or the ionic compound is more likely to dissolve in water. Some exact tips for this: please use the correct sign, especially for the lattice enthalpy. So lattice enthalpy of formation is always exothermic, but it's positive when we are talking about breaking or dissociation. So take note of which one, and when you construct the Hess cycle, just put the arrow whether in the direction of formation or in the direction of the dissociation based on what they provide you with in the exam to determine the two routes. You may also ask about to draw the Hess cycle for the enthalpy of solution, to calculate the enthalpy of solution from data, or explain certain trends like why magnesium chloride is more exothermic than sodium chloride. Remember that magnesium. So what is entropy? Entropy is a measure of the disorder or the randomness of the system. So systems like to have more randomness or disorder, and that will increase the stability. The sample for the entropy is S, and the unit for the entropy is joule per mole per Kelvin. A more disordered systems mean that it has higher entropy, meaning it's more stable. So the more the disorder, the more the entropy and the more the stability. Entropy help to predict whether a certain process will be feasible or not, meaning whether this is going to happen or not. So the increase in the entropy means that we're going to have a higher value for the entropy change. That means that the system or this particular reaction is more likely to take place. So there are certain factors that affect the entropy. The first one is the physical state. So physical states we know is solid, liquid, and gas. Solids are highly ordered, so they have the lowest entropy. Liquids, they have a bit more movement, so they have higher entropy than the solids. And then gases, particles can move freely, so they're highly disordered, so they will have the highest entropy. So the order of entropy, the gas will be the highest, then liquid, then solid. Second thing is the number of particles. The increase in the number of particles, or the more the moles of the product of the gas molecules, means that there will be higher entropy, not just for gaseous molecule, but also for the liquids. So if you have more of the liquids molecules or more moles, then that means you're going to have higher entropy. The increase in the number of particles will increase the disorder and will give a higher delta S, or entropy change. For example, if you have two N2O4 as gas, that gives you two of the NO2 gas. You have two moles of the gas on a product with 1 mole of the gas as a reactant. Then the delta S here is going to be a positive value. There are more moles or more particles, so there will be more disorder and more stability. The third thing is the dissolution. So when a solid dissolves in water, that increases the entropy because the particles will become more mobile. So when you change it from solid to liquid, you increase the entropy, you increase the disorder. So ionic solids, when hydrated in solution, reaction that will give you more disorder and more stability. Entropy change of a reaction. So to calculate the entropy change for a certain reaction, we need to use the standard entropy. So each substance will have a standard entropy at the standard conditions. So the standard conditions is 298 Kelvin as usual and 100 kilopascal. And the standard entropy is the entropy value under the standard condition for 1 mole of a substance. The value will be given in data book and it's in joule this time, not kilojoule per mole per Kelvin. You can use these to calculate the entropy change in a reaction. So the formula for how to calculate the entropy change for a certain system or for a certain reaction, that will equal the total of the standard entropy of the products minus the total of the standard entropy of the reactants. Usually they will provide you in the exam with the standard entropy of the different reactants and products and ask you to calculate the entropy change. You're going to use the standard entropy value from the data book or from the value they are provided with in the exam. And don't forget to multiply by the number of moles in the balanced equation. So when you do this calculation, you're going to have different number of moles for reactants and product from the balanced equation. So when you do the calculation, don't forget to account for the number of moles. Some example, we have the carbon plus oxygen that gives you carbon dioxide as a gas. To calculate the entropy change, the standard entropy for carbon is 9, for oxygen it's 205, and for carbon dioxide 214. We'll notice that carbon is a solid, so it has a very low entropy, while oxygen and carbon dioxide are gases, so they have higher entropy. Now to calculate the entropy change, this is the total for the products, which is just carbon dioxide 214, minus the total for the reactant, which is 1 mole of carbon and 1 mole of oxygen. That will give us plus 3 joule per mole per Kelvin. And this is the entropy change for this reaction. Gibbs free energy is what we use here to judge whether a certain reaction is going to be feasible or not. So Gibbs free energy link the enthalpy change with the entropy change. So it accounts for both. Not only the enthalpy change will be responsible for whether a reaction is going to take place or not, but also the entropy change. So Gibbs free energy, which is delta G, equals the delta H with the enthalpy change minus the T, which is the temperature of this particular reaction. So in Kelvin, multiplied by the delta S, which is the entropy change. The delta G is the Gibbs free energy change, which is in kilojoule per mole. The enthalpy change is in kilojoule per mole. The temperature is in Kelvin, and the delta S is the entropy change of the system as we have calculated it, and we have to change it from joule per mole per Kelvin into kilojoule. So we need to divide the value we usually obtain by 1,000 to convert it to kilojoule per mole per Kelvin. So the feasibility of a reaction, if a reaction has an entropy and Gibbs free energy less than the 0, then the reaction is feasible. So the reaction can occur at this particular temperature. And if it's more than 0, so if it's like endothermic, if it's more like positive side, then it's not feasible at this particular temperature. So what are the factors that affect the feasibility? Some reactions only become feasible at higher temperature because T delta S will increase. So when you have the T delta S, so because delta G equals delta H minus T delta S. So when you increase the temperature and you have the delta S in the positive value, that means this is going to be higher than the enthalpy change and the total of the delta G will be minus, especially when we talk about endothermic reactions, because the delta H for endothermic reactions is positive. So endothermic reaction can occur at certain temperatures because the T delta S becomes higher value. Eventually, the delta G, as we can see, will become a negative, like an endothermic reaction, which has positive delta H. With positive delta S as well, the reaction can become feasible at higher temperature. Some exam tips, always check the units, convert the joule into kilojoule, because this is what we need to do when we calculate the delta G. For entropy of a reaction, don't forget to multiply the entropy values by the moles of the balanced equation. Questions you might be asked to calculate the entropy change of a reaction, as we've seen before, use the delta G to determine the visibility, or explain why the visibility changes with temperature. So how can we decide or determine or calculate the temperature for feasibility? We can calculate the temperature at which a certain reaction becomes feasible if we know the enthalpy change and the entropy change for that particular reaction. In this case, we're going to use the Gibbs free energy equation, but we're going to set the delta G to become 0. So this is the threshold. So this is the minimum value of delta G where the reaction becomes just feasible or the reaction can actually occur. And then when we have the delta G equals 0, we're going to rearrange our equation. You're going to find that the T, which is the temperature in Kelvin, will equal delta H, which is the enthalpy change over the entropy change. For example, if you have a reaction where the enthalpy change is plus 30 kilojoule per mole, so this is endothermic, and then the delta S is plus 100 joule per mole per Kelvin, which is when we divide this by 1000, it's going to be 0.1 kilojoule per mole per Kelvin. Then the temperature will be 30 divided by 0.1, so that